Okay, we are discussing traffic control devices. We have discussed the types of traffic control devices and their subtypes. And then we have continued the discussion with traffic signals. So in traffic signals, we have seen the calculations for the cycle length. Okay, and we have discussed the terms which are used in the calculation as well. This is the last thing which we did, was to discuss some measures of effectiveness for the intersections. Okay, these are the values which tell you about the performance of the intersection. We have used earlier speed, density, flow, these things for segments, for highways. But you cannot use them for intersections because these values don't exist. You are forcing them. When you close a signal becomes red, speed forced to zero, flow forced to zero, and so on and so forth. Okay. So what do we use instead of these values on intersections? We use delay, queue, and stop. What is delay? The difference between the arrival and the departure time. Arrival means you came to the intersection, okay, and there could be a queue in front of you, right? When you will come, you will join the queue, okay, and then after some time you will depart. Depart meaning you will cross the stop line. So from joining in the queue till you cross the stop line, this is counted as your delay. Okay, the difference between arrival and departure, which could include the time you are spending in the queue. Clear? Then we have the queue itself. So queue is measured in terms of number of vehicles. How many vehicles are in the queue? Okay, longer the queue, the worse is the performance. Then stops. Okay, the stop can be used as a criteria using number of vehicles or proportion of vehicles. So how many vehicles stop or what percentage of vehicles stop. Okay, so these are all different measures which tell you about the performance of the intersection. Among them, the most common one is the delay. Okay, the most common measure of effectiveness for intersection is delay. We have discussed it earlier as well in the travel time topic. Okay, delay can be of 4 types. Okay, you have the stop delay, when the car is what? Stop. Okay, that's why we call it the stop delay, right? Yes.
What is the difference between queue and stop? Both are stopping.
Yes, who will tell me what's the difference between queue and stop?
It's the kind of stop.
It's a kind of stop. Okay. Anything else?
Queue is waiting for something to pass, so that it happens. And stopping is for whatever.
Stop time, maybe it's red traffic light, I'm not first. But the queue time, you are stopping, but there is a queue. It's not on this way. There's need to pass the queue.
Okay, it's still, yes. You can move in a queue, right? You can move in a queue, right? So your queue time may include the time when you are moving as well. But you are moving in a queue. Okay? So your stop time could be less and time in queue could be more. Okay? Clear? Got it? Okay? So that means that we have also defined this one, time in queue delay. The time when you are what? When you are in the
Queue.
somebody say. Yeah, you are in the queue, okay? And which one could be higher? Stop or time in queue? Huh? Which one could be higher than the other one? Stop delay or time in queue delay?
Higher in time, you mean?
Yeah. Stop delay or time in queue delay? Which one could be more than the other?
Depends.
Stop?
The queue is
I am saying could be. I am saying could But which one could be higher than the other? Huh? Q. Time in Q delay could be higher. Your stop delay could be 0, but you may still be in the queue, right? So you joined, when you came, the signal became green. So you actually didn't have to stop. But they were 5 meters in front of you. So you are in the queue. Okay, so you may have 0 stopping, but still time in queue delay. Okay, so time in queue delay could be higher. Okay, then we have this one, which is called as the approach delay. Again, we studied the same thing in the travel time topic and we gave it the name control delay. Control delay and approach delay means the same thing. Control delay and approach delay means the same thing. Okay? They include 3 things. Control delay or approach delay includes 3 things. They are mentioned here. Tell me what?
Acceleration.
Huh?
Acceleration and
Acceleration, deceleration and what else? Stopping. Okay, so when you are coming to the intersection, you see the signal, you see the stop sign, whatever, and you start to decelerate. Your approach delay started. Okay, you may have to stop. If you stop, if you don't stop, then you once you cross the intersection, you accelerate back to your normal speed. Then all of this is counted as approach delay. Okay, what other name we have given it?
Control delay.
Control delay. Okay, means the same thing. Okay, then we have the last one, which is called as the travel time delay. Travel time delay, whether it's an intersection, whether it's a highway, it has the same definition. Okay, which is the difference between the actual travel time and desired travel time. Okay, the difference between actual and desired. Actual means whatever you observe. Okay, so you can actually observe the actual travel time with a stopwatch. Okay, how much time is actually taken by the car to cross? Okay, that is actual. But how do I get the desired travel time? How can we measure something we desire? We measure it using a speed limit, right? We desire the speed limit. Yes. How do we put the speed limit? That is one thing, you can do it. This is one approach you can do. Okay, yes. Take the actual time, calculate the delay, subtract the delay, you will get the desired one, right? Subtract the other delays, you will get the desired one. Okay, but that is not always the case. That is not always the case.
Isn't joining an intersection the same as stopping in the intersection?
Sorry?
Isn't stopping, joining the intersection the same as stopping the intersection?
Not always.
When you join, you don't stop.
You may not stop. The signal is green. Why would you stop? Okay, but you cannot keep on moving because there are cars in front of you. Yes, coming back to the question, how do we get the desired travel time? One approach is you take the actual one, then subtract the time in queue delay. You may get the desired travel time, but not always. We said use the speed limit. How do we get the speed limit? Huh? Design. Okay. How do I know about the design speed? Which speed is called as the design speed? We have used it in the calculations.
Directional design only one.
Speed. Which speed we call as the design speed? Free flow speed. Okay. So the desired travel time comes from free flow speed. Okay. And this is why I said that you subtract the delay, still you may not get the desired travel time. Because your speed may not be free flow speed, right? It's not like you're always going at free flow speed. Okay? Maybe you are coming for my class, so you're not in a mood, huh? Take your time, right? You're hoping the signal becomes right, huh? So, the desired travel time comes from the free flow speed. Okay, so the actual is actual, and desired comes from free flow speed. And you can do it for any part of the road, whether it's an intersection or whether it's a segment or whatever. Okay, you get the travel time from the free flow speed. Okay, this diagram shows the 3 types of delay. We have total 4. The one which I showed you in the previous slide were 4. Okay, you can count it. You did, right? Okay. So 3 of them are here. We have time on the x-axis, distance on the y-axis. You can see a line here which says desired path. So desired comes from which speed? Free flow speed. Okay. Now what is the speed? Speed is a ratio, right? Ratio of distance over time. Okay. Which means the slope, right? So you draw a line according to the slope of free flow speed. That is my desired path. Then you see another line which shows the actual path. Okay. The difference between actual and desired, what did we call it? Travel time delay. Okay. I just realized in the other section, if I keep on pointing at the slides, you may actually read them. Okay. I found it after wasting 10 minutes. So I'm getting smarter. Okay. Okay, not you guys. We are saying. Okay. Travel time delay. Okay, the difference between the actual path and the desired path. Okay. Then you see here, the vehicle is going at some speed. What is happening here?
Breakpoint.
Huh?
Breakpoint.
Breakpoint. You have started reading for the quiz, right? Forget about it. Direction, design, novelty, volume, breakpoint. Where is the breakpoint? What is happening here?
Reduce the speed.
Reducing the speed. Okay. And what is happening here?
Q.
Huh?
Q.
Stop it. Okay. Stop it. Okay. And what happens here?
Acceleration.
Acceleration. Okay. So this is what we call as stop delay. And if you add this part and this part, deceleration, acceleration into the stopping, then we call it approach. Clear? Okay, so we can see 3 of them here. The 4th one is the time in Q delay, which can be shown here. Again, time on the x-axis, cumulative vehicles on the y-axis. Cumulative vehicles on the y-axis. Okay? You can see here the time axis is divided into green and red intervals. Okay? So when the signal is green, the vehicles are moving, right? Okay? So you see the movement of the vehicles, the line is going up. The signal becomes red, then you see the line is divided into 2 portions now, 2 branches. Okay? This one shows the vehicles leaving, departing the intersection. Vehicles leaving or departing the intersection. When signal is red, are any vehicles leaving? No. You see the line goes straight. No vehicles leaving or departing. Okay. The other branch shows the vehicle arriving, coming. Okay. So even when the signal is red, this line, then it stop, right? Vehicles arriving or leaving, they don't stop. Okay. Then the signal becomes green, and then what happens? This line starts to go as well. Departing also starts to happen. Okay, and then you see the 2 lines meet here. When the arriving meets departing, all vehicles coming and all vehicles leaving, they are the same now. So what became 0? Q became 0. Okay, so at that point the Q became 0. Okay. So that also means what? When these lines were not equal, there was a Q. How much is the Q? The difference. Okay. So this is the Q. The length of the Q. How many vehicles are in the Q. Okay. Then if you want to see, for example, this vehicle I, which arrived at any time during the red. Okay. So it arrived at this time, and it left the intersection at this time during green. Okay, so this time was spent where? In the Q. Okay, so this gives you time in Q delay. W is the time in Q delay, or the waiting time. Another name for it is the waiting time. Okay, so you can get the waiting time or the time in Q delay for any vehicle from here. Clear? Okay, any questions? Okay, there was a scientist, traffic engineer, whoever you call it. His name was Webster, and he gave this equation for calculating uniform delay. Okay, delay at the signal. Why he called it uniform delay? Because this is the delay because of signal timing. Okay, it does not take into account the length of the queue. Okay, it does not take into account the length of the queue. Okay, but we know the length of the queue has an effect, right? If you keep the signal timing same, but the traffic keeps on increasing. So traffic increases means the queue will be longer. Okay, so will you have the same delay? No. Okay, the delay will increase, right? But his equation doesn't take into account that factor of the long queue. Okay, so that's why it's called the uniform delay, because it does not take into account the traffic conditions. Traffic conditions are changing, right? Don't change the signal timing, the delay according to his equation remains the same. So that's why uniform, because it remains the same. Okay, so he gave this equation in 1958 when I was young, and I'm still teaching it. Okay, so according to his equation is half R into V. Okay, R is called the effective green time. Oh, sorry, effective red time. R is called the effective red time. Okay, and V is the number of vehicles in the queue. Okay, R is the effective red time, V is the number of vehicles in the queue. Okay, if you look at this diagram, actually you will know how or why he is saying half R into V. Which triangle? Between what? The Q. Maafi Q. Between what?
Free flow speed.
The quiz will be very good. I should include this in the quiz as well. Free flow speed. Where is the free flow speed? It's vehicles and time. Between what? Triangle between what? You were saying something?
In the red phase.
In the red phase. But between these two lines, the arrival and the departure line. Okay? Arrival and the departure line. Okay? Anyways. So, half R into V. V is the number of vehicles in the queue. V is the number of vehicles in the queue. Okay? R is effective red. V is the number of vehicles in the queue. Okay. For R is part of the cycle, right? Effective red is part of the cycle. The total time is cycle length. Okay? And R is part of it. The other part of cycle length is called effective green. Okay? So G upon C gives you proportion of cycle length, which is effective green. This thing. And 1 minus this will give you effective red. Got it? Clear?
Effective degree will be from start to degree to the other start.
Sorry?
Effective degree from the start of the first degree to the start of the other, right?
No. Effective green is phase time minus lost time.
Okay.
Now we are talking about total here. Total. So simple total cycle length minus total lost time. Effective green. Okay. I already told you previously, but you will forget again. So I will not discuss it next time. Okay. Okay, so effective green, 1 minus this will be effective red. So multiply by cycle length to get the time. Okay, so now we have equation for effective red. We have an equation for effective red. What is the other parameter I need? V, right? What is V? Total number of vehicles in the queue. Okay. Where is the queue? Queue starts from here and ends where? Okay. How much time is this? R plus TC, right? So it starts from the start of R and it ends at the end of TC. R we know is what? Effective red. TC is called the clearance time. TC is called the clearance time. So after write, it will take TC seconds to clear the queue, for the queue to become 0. Okay. Now, this is the line for arrival. Okay. So the slope of this line is number of vehicles upon time, right? Flow rate. Okay. So this small v is the flow rate of vehicles arriving, coming. Small v is the flow rate of vehicles arriving or coming. Okay. Now I want vehicles in which time? R plus TC, right? So small v, vehicles per unit time, multiplied by R plus TC, number of vehicles in the queue. Got it? Okay. Then we have another line, right? We have two lines. This line has a flow rate. Here, do I have any flow rate here? No, it's 0, right? Because there is nobody leaving. Here we have flow rate, okay, which is represented with S. S stands for saturation flow rate. Okay, S is saturation flow rate. Okay. If I want to use this to calculate the vehicles in the queue, now at S starts from where? Okay, and when does the queue become 0? At the top. How much is this time? TC. How much is the slope? S. So S into TC should give me the same value, right? Both lines are becoming 0, right? Okay. So if you use this flow rate, small v, then it will be small v into R plus TC. If you use this line, the departure line, it will be S into TC. Clear? But at that point, both of them are equal, right? Both numbers are equal. So this is what they did here. Okay. And from here, they derive the equation for TC. Now remind me, TC was which time? Time to clear the queue. We call it the clearance time as well. Okay. Now remember, we are doing it for calculating number of vehicles in the queue. Okay. Number of vehicles in the queue. Okay, number of vehicles in the queue can be this or it can be this one, right? One of them. Let's say it's this one. Okay, number of vehicles in the queue, this one. I have R, I have TC. For R, do I have an equation?
Yes.
Yes. Okay, for TC, do I have an equation? No? What is this? Like I said, if I keep on pointing at the slide, you will actually see it. Right? Okay. So I have an equation for R, I have an equation for TC. I can put both these equations, the V equation. This is V, right? Number of vehicles in the queue. Capital V is number of vehicles in the queue, which is equals to small v into R plus TC. I have an equation for R, I have an equation for TC. If I put both these equations, V becomes this. Okay. Now why I am doing this? To calculate uniform delay, okay, which was half R into V. Now R has an equation and V also has an equation. So I put both these values together. This is the equation for the final uniform delay. Okay. This is the uniform delay equation according to Webster. Okay. So it was actually this, which was very simple. We didn't like it. We changed it to this one. Okay, we don't like simple, right? That's why you guys are here. Your lives were very simple at home. Okay, clear? Now this equation gives you aggregate delay, meaning total. This equation gives total delay. Okay. If you have total of something and you want average, what do you do? Summation by number, right? In this case, summation, so this is already the summation, right? Total. Divided by number of vehicles. Okay. So this divided by number of vehicles. This is the equation for average delay. Uniform average delay. That the first one is for uniform aggregate delay, the last one is for uniform average delay. Okay, the first one is seconds vehicle, and the last one is second per vehicle. Clear? Okay. Okay. Now this equation, now we have V by S. Okay. Which again looks very simple, right? Which we don't like. We'll change it. Okay. So V is the demand, the flow rate coming, right? The flow rate coming. S is the saturation flow rate. Instead of saturation flow rate, we want capacity here. Okay. Instead of saturation flow rate, we want capacity. Okay. Anybody remembers what is saturation flow rate? Maximum flow rate, and what is capacity? Maximum flow rate. What is the difference between them? Nothing. Yes. Anybody? What is the difference between them? Which one is exceeding the maximum capacity? Saturation is higher. Why it's higher? The answer is correct. But why saturation is higher? We are discussing what is the difference between capacity and saturation flow rate. Demand can exceed capacity. Yes. That is the actual. But what is saturation? Sorry? No. Again, something I wasted my time on earlier as well. Saturation flow rate is the maximum flow rate without considering any lost time, without considering any stopping time. So that is the saturation flow rate, that is the maximum flow rate without all these things. Capacity is maximum flow rate with these things. Okay? And we did one example earlier, okay, in which we use the relationship which you see in the first line. Capacity equals saturation flow rate into G by C ratio. Okay? Saturation flow rate, as I already explained, small g is effective green. Okay? Effective green was what? Cycle length minus lost time. Okay? Cycle length minus lost time. And capital C is the cycle length. Okay? So the actual capacity is saturation flow rate into the proportion of cycle length, which is effective green. Okay? If there is no lost time, your capacity equals the capacity equals saturation flow rate. If there is no lost time, this is the difference between saturation flow rate and capacity, right? Okay? Capacity has lost time and everything, all the types of delays you have. Okay? And saturation flow rate doesn't have it. Okay? So, if I don't have any lost time, then effective green is equal to cycle length. Then capacity equals saturation flow rate. Okay? But this is not the case. We have lost time. So this will be a ratio, and your capacity is saturation flow rate into this ratio. Okay? So, anyways, in the equation we have V upon S. Okay? There we had V upon S. I am trying to replace S here with capacity. So capacity equals S into G by C. Then S equals capacity upon G by C. Okay. So it was V by S here. Now I put this equation, it becomes this thing. Okay. Clear? Small g effective green. Capital C cycle length. V, small v, arrival rate, demand. Okay. Small c, capacity. Okay. And instead of writing V upon C, demand upon capacity, we often write X. V upon C can be replaced with X. X means V upon C. Okay. And we have used it in another delay equation, which was for the roundabout. Okay. The roundabout delay equation also has X, and that X also means V by C ratio. Okay, clear? Okay. We have an intersection approach, flow rate is given, saturation flow rate is given, cycle length is given, G by C ratio is given. They want average delay per vehicle. The equation for average delay per vehicle is this, what you see on the board. The final form. Do I have everything I need? Is there anything missing here? Effective green. Do I need it? What do I need in the equation? I need the ratio, right? And the ratio is given. Anything else missing? Yes. Nothing is missing, then give me the average delay. Wave cycling 90 seconds. Okay, what else? Everything is there. Give me average delay. Huh? Capacity is not given. So you cannot calculate what? Huh? The ratio, B by C ratio. You cannot calculate X. How do we calculate capacity? Yeah. Okay, this thing. Okay, saturation flow rate into G by C ratio. Okay, capacity is saturation flow rate, which is 2800 into G by C ratio, which is 0.55. So how much is this? 1540. Okay, now the X B by C is how much now? How much is X? So my V is how much? What is my V? 1000. Huh?
100.
Sorry?
100.
Okay. Okay, any problem? Any questions? Clear? Okay, so this is how we calculate the average delay. Okay, continuing with the same topic but from a different chapter now, we will move on with more calculations related to the design of the signal. The signal design process follows 3 steps, okay, and then there are subtasks with the steps as well. You can see step 2 and 3, it has more than one activity. The first step is to develop the phasing plan for the signal. Phasing plan means you decide which movements are allowed together to go in one phase. Okay? Phasing plan development means you decide which movements are allowed together on the signal. Okay? And you decide their sequence as well. Okay? So which movement will happen first, and after that which one the next, and which one the next, and so on. Okay, so these are the two things you decide: the combination of movements and their sequence. Okay, and in this case there is no calculation. For the first step there is no calculation, you are planning. Okay, so this is part of your planning, there is no calculation for that step. Next one, the next step has how many? 5 tasks or 5 activities. It includes calculating all timings of the signal, all types of timings. Okay, so you start with calculation of yellow and all red. Then you need to calculate the volumes in the critical lanes. Then you move on to calculating lost time for every phase, lost time for the cycle, and then you calculate the cycle length. Now we did only this part in the last topic. Okay, so for that we already have an equation. We are going to use the same equation. Okay, but you can see there are many other steps as well. So you know the total time now for the signal. You divide this total time for each phase now. Okay, how much from the total time you will give for each phase. Okay, that is the last step. After you have done this, then we move on to the next step, which is the pedestrian check. Okay, obviously signal is at the intersection. When the signal will become red, the pedestrians will also try to cross. Okay, so you need to check is red time enough for them to cross. Okay, so first of all you try to find out how much time the pedestrian needs to cross. Okay, then you compare between that time and the time you are providing him or her to cross. Okay, and which one should be higher? The provided time of the signal should be high. Okay, if it is not, then you have to adjust. Okay, obviously you will adjust the signal time again. Okay, not the pedestrians. Ask them, run. Or you will die. Okay, so the last step is the pedestrian check. So we just discussed the first step today, which is the phasing plan. As I said, there is no calculation for it. So you cannot get any fixed answer that this is the phasing plan, you should always have this. Okay, the phasing plan is not fixed. You can come up with your own plan for every intersection, which can be different. Okay, but you have to keep these few points in your mind. The first point is the movement which you are allowing together. Okay, you have to allow that combination which has minimum risk of accident, right? You cannot allow two movements which are conflicting with each other to go together, right? Okay, clear? So find out the combination of movements which has least accident risk. Okay. Secondly, you have to follow some standards and criteria for providing control devices at the intersection according to your phasing plan. For example, if you decide I will provide a separate phase, or before that, going back to the first point. So I said that we try to minimize the accident risk, okay, by allowing different movements in different phases. Okay, but that could also mean you will increase the number of phases, right? One phase for this movement, one phase for this one phase for this one. Let us have all movements in different phases then. Zero accident risk. Okay, but every phase has a lost time. When you increase the number of phases, you are increasing the number of lost times. Okay, so you are making it safer, but you are also increasing the lost time. Okay, so you have to compromise between these two things, safety and time. And time is money, so let people die. So the next point I was making is other control devices you have to use at the intersection according to your phasing plan. So for example, you decide I will provide one phase for straight and a separate phase for left turning. Okay, so there are two phases, one for only straight, the other one for only left turning. Okay, now with this phasing plan, what are the things I have to do at the intersection to make this happen? to make these two phases happen at the intersection in different times. Huh?
Control the other.
We what?
Control the other.
No, no, at this approach. What do I have to do at this approach?
Control device.
Which control device? Like
Arrows.
what would you put?
Um,
Arrows. So you need lane markings with arrows, right? Okay. Anything else? Huh? You need a separate lane. You cannot have a lane which has straight and left both. Okay. You cannot have a shared lane. Okay. Anything else?
Great.
Huh?
Great. Higher.
Higher what?
Put the other name higher. Like a bridge.
No. We are talking about signals. Yeah. I don't have money for the lane. Yes. What else? Anything else? Separate traffic signal, okay, both directions. So you will have two poles with two different signals, one for left turning, one for straight. That's how the driver would know that I have a different signal which I have to follow, okay. And sometimes you will see a traffic island between the two lanes as well, okay. So all these things are done because of what? Because of the phasing plan, okay. So you have to, once you decide the phasing plan, you have to also design the control devices at the intersection accordingly. Clear? Okay. The last point you have to keep in mind is the intersection geometry and the volume requirements. Okay. You may have a T intersection. You have intersections where the roads are not meeting at right angles. You have intersections where maybe more than two roads are meeting. You have more than 4 directions. Okay. So you have to keep all these things in mind while you are deciding the phasing plan and the volume as well. And we talked about number of lanes, right? So I want to provide an extra lane, but there is no space. What should I do? Okay, I have to change my phasing plan. Okay, and volume requirements. Usually, we don't try to combine heavy movements together in one phase. Okay, we don't try to combine because that can create a lot of problem and that can result in crash. Two heavy movements happening at the same time, we don't usually prefer it. Okay, so the volume should also be considered when you are deciding the phasing plan. Okay, once you decided the phasing plan, you can show it by means of one of the two diagrams. One is called as a phase diagram, the other one is called as a ring diagram. Okay, so we have a phase diagram and we have a ring diagram. Both of them are showing the same thing but in different manner. Okay, in the phase diagram we show all the movements which are happening together. Okay, all the movements which are happening in one phase together. In a phase diagram, all movements of one phase are together, irrespective of their direction. Okay, wherever they are happening, but we will in the phase diagram, because they are happening at the same time, they will be in the same box for the phase diagram. In the ring diagram, all movements which are happening in the same phase in one direction will be together. Okay, all movements which are happening in the same phase and the same approach will be together. Okay, so in the phase diagram, they are together irrespective of the approach. And happening from here or there doesn't matter, but they are happening together, they will be together. Okay, in the ring diagram, okay, so if I have movement from here and movement from here, there are different approaches, right? So in the ring diagram, they will be shown separately. Okay, now this is the east side, this is the west side. Okay, so I cannot have one signal for both of them, right? I have to put two different poles for these two sides, right? Okay, so the ring diagram will show this one separately and this one separately. This is called as a face of a signal, face. Okay, so in the phase diagram, we show all the movements of the phase. In the ring diagram, we show all the movement of a face, side. Okay, face meaning side, approach. Clear? Okay, let me show you some examples before we move on, but some notations we follow in the phase or the ring diagram. By the way, a ring diagram is more common. Okay, ring diagram is more commonly used. Okay, these are the notations we follow in these diagrams. Basically, arrows. Arrows are showing the movements. Okay, now you can see in the second one and the third one, you have the arrows from the same line. Arrows from the same line means they are in the same lane. Okay, so all movements, 3 of them in the same lane. Okay, here, fourth one, how many lanes I have? 2 lanes. Okay, if I have one more lane, then I will have another line. Clear? Okay, then you see some arrows have dotted and some arrows have solid lines. Okay, yes. Okay, the dotted one is what we call as permitted. Okay, the dotted one is called permitted. Okay, which happens if you have the chance. Okay, so for example, you are taking a right turn. Okay, so you wait for your chance. Whenever you get the chance, you make the right turn. Even if the signal is red. Okay, so this is what we call as permitted. The other one, the solid one, is what we call as protected. So this happens only for at the signal, because of the signal. This happens with the green signal only. Okay, signal is red, you will stop. Even if you have nobody from the other direction, cannot make this movement. Clear? Okay. Now some examples for the phase in the ring diagram. You see the first one, I have 2 phases. Movements are happening from different directions, but they are shown in the same phase. Okay, here and here. How many phases I have? 2. If you look at the ring diagram now, what happened? Same movements, but they are shown differently because they are happening on different sides. Okay, how do I know they are in one phase? Because they are parallel to each other. Okay, so these 2 movements are in the same phase because they are parallel. Okay, so this is one phase and this is another one. Okay, another example. What changed here? Tell me how many phases? 3 phases. Which phase is the extra one? Extra phase is for which one? For the left turn. Now you look at the intersection now. Do you see any change in the intersection? There's an extra lane for left turning now. You have to provide an extra lane for left turning now. Okay, you cannot make it from the same approach. Okay, and again you see different movements in ring diagram, different approaches are different, and in the phase diagram together. Okay, the last one is this one. Again, you see how many phases? 3 phases. Okay, which diagram is it? Ring or the phase? Phase diagram. Okay, you can, for practice, you can make your own ring diagram for this. Okay, but now you know what's the difference. Okay, and how to make it. What is happening in the extra phase? You see any movement? Okay, so that is the, sorry, clearance for who? Pedestrians, yes. Okay, so this is the pedestrian phase. Okay, they are providing an extra phase just for pedestrians. Obviously not common. It is not common. Okay, pedestrians will move with the phase, obviously. Okay, but for extra safety, you can do something like this. Okay, and especially when you are allowing multiple movements at the same time, including the turning, this could be dangerous for pedestrians. You see, the turning movements are permitted. See, so when do the pedestrians have a chance to move? Okay, so that's why they had to do this. Okay, otherwise you will not see this commonly. Okay, any questions? Okay.